You know, some math problems, they look so simple on the surface, don't they? But they're actually hiding a secret. They're these little puzzles where your usual bag of tricks just won't cut it. And today, we've got one that needs a very, very special weapon to crack. Let's take a look. All right, here it is. 2 to the power of x plus x equals 5. So, take a second. Look at it. What's your first move? I bet you're thinking, okay, just get x all by itself. And yeah, that's the obvious first step, right? Well, that's exactly where the trouble starts. See, the whole issue, the reason this is so tricky, is that x is playing two different roles at the same time. It's hanging out down here in the main equation, but it's also stuck way up there in the exponent. And your usual tools, factoring, just taking the log of both sides, they're not going to work. You can't untangle it that way. And that's what makes this so cool. So where do we even begin? Well, with any puzzle like this, you start with what you know, right? Let's just push normal algebra as far as it can possibly go and see where we get stuck. Okay, so the most logical first step is to get that 2 to the x term by itself. Easy enough. We'll just subtract x from both sides, and boom, now we have 2 to the x equals 5 minus x. All right, not bad. A good, clean start. Now, the next instinct is probably to get all the stuff with x onto one side of the equation. A pretty standard way to do that would be to divide both sides by 2 to the x. So when we do that, we end up with this. 5 minus x times 2 to the negative x, and that whole thing equals 1. Okay, and we've hit a wall, a total roadblock. Look at it. We've got x stuck in that 5 minus x part, and it's also trapped up in that 2 to the negative x exponent. We literally can't isolate it from here with our standard toolkit. Algebra has officially tapped out. So, what on earth do we do now? We need something else. Okay, so when your normal tools just won't do the job, you have to call in a specialist, right? It is time to pull back the curtain and show you the secret weapon. It's a special function that was basically invented for this kind of messy situation. Say hello to the Lambert W function. So what is this thing? The Lambert W function. You might also hear it called the product logarithm. It has one very, very specific job. It's designed to solve equations that are in this exact form. A times e to the a. That's it. Some number, let's call it a, times e raised to the power of that same exact number. And here's where the magic happens. If you can twist your equation into that perfect form, a times e to the a, the w function acts like an undo button. You apply it, and the whole complicated mess just dissolves, and it spits out a clean, simple a. It basically frees the variable from that exponential prison. Think of it this way. That a times e to the a format, it's like a really unique, specially designed lock. Right now, our equation doesn't look anything like that lock. It's just a lump of metal. But our job is to become a blacksmith. We have to heat it up, hammer it, and forge our equation until it perfectly matches the shape of that lock. Because once we do, the Lambert W function is the one and only key that fits, and it's going to unlock the whole thing for us. All right, so our mission, should we choose to accept it, is clear. We're going to take our equation, the one that got us stuck, and we are going to meticulously reshape it step by step until it becomes that perfect a times e to the a form. Now, this whole forging process is going to happen in 3 big steps. First up, we've got to make the part on the ground match the part up in the exponent. Step 2, we need to get the number e in there somehow because the w function won't work without it. And for the final step, we'll do one last little tweak to get the form absolutely perfect. Okay, let's dive in. Step 1, making those parts match. If you look at our equation right now, we've got 5 minus x out front, but the exponent is just negative x. They don't match. So here's a clever trick. We multiply both sides by 2 to the 5th. When we do that, we can combine the exponents on the left. And check it out. Now we have 5 minus x times 2 to the power of 5 minus x. They match. And the other side, 1 times 2 to the 5th, that's just 32. Beautiful. All right, one hurdle down, but there's a big one coming up. The Lambert Y function is a bit of a diva. It only works with the base e, not 2. So what do? Well, luckily for us, there's a fantastic little math identity that says any positive number, let's say 2, is the same as e raised to the power of the natural log of 2. It's a bit of a mouthful, but it lets us do a substitution. We just swap out that 2 for e to the ln of 2. And just like that, e has entered the building. Okay, we are so close, I can taste it. Look at what we have. The exponent is now the natural log of 2 times 5 minus x, but the term out front is just 5 minus x. It's almost perfect, but not quite. The term on the ground needs to have that natural log of 2 as well. So what's the final move? We just multiply both sides by the natural log of 2. And there, it's done. Look at that left side. We have the natural log of 2 times 5 minus x, all times e raised to the power of that exact same thing. That is our a times e to the a. We forged the log. Whew. Okay, the hard part is over. The metal has been hammered into shape. The lock is ready. Now, it's time to get the key and open this thing up. So here we go. We take our key, the w function, and we apply it to both sides of the equation. And on the left, because we did all that hard work to get it into the perfect form, the whole thing just collapses. It simplifies beautifully, leaving behind only the a part we worked so hard to create. And this is what we're left with. On the left side, all that's left is our a, which was the natural log of 2 times 5 minus x. And on the right side, we have w of 32 times the natural log of 2. And all of a sudden, look, this impossible problem is just a basic algebra equation now. We can actually solve this. So we just do a little bit of rearranging, divide by the natural log of 2, move the 5 over, solve for x, and we get our exact answer. Now, it looks a little crazy, I'll give you that, but that is the 100% mathematically perfect solution. Of course, for most of us, we want a number we can actually use, right? So you can plug that into a calculator and get a much friendlier approximate decimal. And that number is about 1.716. There it is. After all that algebraic blacksmithing, after finding the secret key, we have our solution. That is the number that makes the original equation true. It really makes you think, doesn't it? This problem felt completely impossible using the tools we all learned in school. But the moment we found the right tool, it just clicked into place. It kind of makes you wonder, what other problems that we think are impossible, whether it's in math or science or anywhere else, are just sitting there waiting for someone to come along and invent the right key?